And that was Rainy Days and Mondays by music by Roger Nichols. And popular by the Carpenters. Now we're going to get into Ocean of Color by Philip Wesley. I play a Lion in Healy Prelude Lever 40 harp, so I am changing the notes with levers instead of with my feet. Here we go. And as we leave our ocean of color, we are going to enter the approaching night by Philip Wesley. And once again, I'm changing the keys with levers.
Kim. I think we're ready to get going. Thank you so much again. We really appreciate it.
Thank you.
Um,
Thank you so much.
great beginning to our meeting. Welcome everybody. This is the March meeting for Orange County Astronomers. We theoretically are getting close to spring, but you couldn't really tell that by the weather we've been having recently. And I know that people that are or we're hoping to go to the in-person meeting at Chapman may be having problems with the weather. I hope nobody is really having too many problems. Wish you well. I'm sorry I can't be there myself tonight, but hope to see you next month. And I would like, before I turn this over to the our announcement people, I would like to remind people that this is the month, if you're going to do the CA Marathon, when you can actually do that. Our star party is very close to the equinox, which is about the best time for doing the marathon. And there are forms for doing that on the website. And without more ado, I will turn the meeting over to Kyle Graham for the announcements. Thanks, Kyle.
Awesome. Thank you. All right. So welcome to the March 10th meeting. Welcome new members. If you're currently present at the in-person meeting, you'll be able to pick up your badge either this month or next month on the whiteboard. Otherwise, it will be mailed to you. Just once again, these are the results of the election. These are your 7 trustees, president, vice president, secretary, and treasurer for the 2023 year. Star parties continue to check the website for details on dates and times for those, and those are available. The astrophysics special interest group meeting again in person at the Heritage Museum on March 17th. Beginners classes in person April 7th. And then the OCA board meeting is online May 7th. You can check the website calendar to join online events. The Zoom link will be available. For our outreach events, we have a new outreach coordinator. Please join us in welcoming Jeff Gray. You can reach him at outreach@ocastronomers.org. For those who are in person tonight, the coffee stand is open, selling coffee, donuts, and water. It's just up top by the library where you came in. Feel free to grab snacks and enjoy them during the meeting. The Adopt Scope program is back up and running. You can look at the current inventory and download a sample adoption agreement online, as well as there's some information about the program there if that interests you. We're always looking for new content to go in our Serious Astronomer newsletter. So please contact Dave Fisher if you have any content that you think would be interesting to have put in there, and he'll review it. His email is there, newsletter@ocastronomers.org. Once again, if everyone gets an in-person printed copy mailed to them, but if you would like to opt out of receiving a mailed copy, please email Charlie. Everyone can always access the newsletter online on the website. And again, say that everyone gets a mailed copy unless you opt out. Remember to please keep your pad clear at ANSA of weeds. Do remember that even if we're not having star parties as regularly out there, we still need to make sure that the weeds get kept clean and cleared. So please keep your pad clear, and if you can help in any of the other common areas, that would be really appreciated. So the next meeting will be held on April 14th, and I'll turn it over to Alex McConaughey for the What's Up presentation.
So thank you very much, Kyle. We're waiting for the in-person crew on the ground to connect so that the WhatsApp presentation can be conducted. We have Alex McConaughey from Riverside Astronomical Society doing the WhatsApp presentation for us this evening. Crew on the ground, if you're ready, we are ready for you to start the presentation. Looks like the computer that needs to join the webinar as a panelist has not joined us yet. I apologize for a few minutes of delay as we are reestablishing our connection with the ground.
Well, everybody, it looks like John Hoot's computer is joining, so hopefully we'll be back online in a moment. Please bear with us, and thank you for your patience.
Okay, John, you're with us and need to open up your video and audio. John, if you can hear me, we do not have your, your audio is on. Okay, let's see, we're working out.
But are you seeing our screen here?
Yes, your screen
right.
is showing.
All right, I think we're ready. We'll try one more time.
Can you hear me out there?
Yes, we can hear you clear, John.
Okay.
And I just think you need to disable your background, John. Everything else is fine.
Too many cooks.
We want. Well, first off, let me start the presentation again. Here. What's that? I'm ready to start presenting. Can you see my presentation screen? Oh, you should not be that far along. You guys are seeing things you shouldn't be seeing yet.
Yeah, we're not seeing your screen yet.
You are not seeing my screen? Click OK.
Not at the moment.
Try that. Back to Zoom.
There is quite a bit of
This is the one I
interference
want to share. Yes.
but with the background,
they
it
did-
looks
they
like
were
it's
cool about that.
interfering
Now
with.
can you see it? Now can you see my
Not yet.
title screen, Reza?
No, we cannot yet.
Go to that screen, actually move, yeah, to Zoom and share your screen.
Okay, well, let's get it up there first. That's there. Okay, my cursor's over there. Okay,
That's not what we want. We need to go to Zoom.
So again, we apologize for the delay you're experiencing. The crew on the ground will be up and running pretty soon. Just a few technical difficulties in the hybrid mode.
I'm cursing. Reza?
Yes. We're not seeing your screen share yet.
Yeah, that's what. No, it's way down here. Once we get to Zoom. Press a bit.
Okay, there we go. We have you. And as the final thing, if you could change your video background so that we can have a full view, that would be best.
I think that's pressing our skills right now.
Okay.
It would be nice to just get the screen shared and get the presentation going in the right direction. Do you want to be on your notes? All right, let's get your notes. Okay.
Not so critical. I get to the notes. I can take it. It's fine. Control. Try to-
Again, thank you for patiently waiting. Let me assure you that we actually have done multiple rehearsals before this, but Zoom never fails to surprise. We thought we had it figured out last time. It was working perfectly. Now we're encountering problems again. So we apologize again, and we assure you that we're working our best not to let this happen again.
Reza, we're struggling enough
Yes.
here that we should probably bring the main speaker on and we'll correct our problem. And if there's time at the end, we'll give the what's up.
Okay, sure. So let me go into introducing our main speaker tonight. Our main speaker at this meeting completed her PhD at the University of St. Andrews in Scotland, where her thesis focused on searching for exoplanets in open clusters. This work led her to her first postdoctoral position at Queen's University, Belfast, Northern Ireland, where she was a founder member of their Super WASP Transit Survey, for which she received the RAS Group Achievement Award and a PPARC postdoctoral fellowship. Rachel considers herself fortunate enough to have joined Lascumber's Observatory, LCO, soon after it was founded, giving her the opportunity to watch the LCO telescope network develop into full operation. Rachel started to study first exoplanets and later solar remnants through the phenomena of microlensing using LCO's telescopes. And she now leads the LCO's microlensing group as a senior scientist. She recently stepped down as a co-chair of the Rubin Observatory Transients and Variable Star Science Collaboration, which aims to prepare for groundbreaking science with the legacy survey of space and time. Please join me in welcoming Dr. Rachel Street. Rachel.
Thank you very much, Reza, and thank you everybody for having me. So thank you very much for the invitation, and let me get started by sharing my screen. So hopefully you can all see my slides there.
We can see it all perfect. And since we did check, did you enable the shared computer sound also option?
Yes, I remember to check the box. So hopefully that will come up later in the slides. Thank you very much.
And we are all ears for your presentation.
Thank you. And hello, everybody. It's a pleasure to talk to you today, and I'm sorry I can't be there in person, so I really appreciate the organizers making it possible for me to join you on Zoom. So today I'd like to talk about some of nature's most elusive but fascinating objects. Before I go any further, however, allow me to credit the lead of the program I'm going to discuss today, Kailash Sahu from the Space Telescope Science Institute, and the rest of his multinational team. I'll be introducing work by our team and many others throughout this talk. So black holes have been a science fiction staple for years as mysterious regions where gravity distorts space-time so strongly that even light cannot escape. But the concept dates back perhaps further than you might think. Black holes were originally conceived as far back as the 18th century by John Mitchell and Pierre-Simon Laplace as the theoretical consequence of a gravitational theory under the most extreme but naturally occurring circumstances. These predictions were subsequently reinforced and refined by general relativity, and so the detection of black holes is one of the signature tests of that theory. Now, in practical terms, black holes are predicted to be strikingly simple objects. All mass is crushed into the central singularity, and around this is a radius beyond which the velocity needed to escape the gravitational pull exceeds that of the speed of light. This is often called the event horizon, but it's important to note that this is more a characteristic radius than a physical boundary. They typically have just three properties: mass, electric charge, and angular momentum. And since they are not self-luminous, they are notoriously hard to find. But so what? All of this is very curious, but what can we actually learn from them? Well, it turns out that these enigmatic objects could be quite revealing. Firstly, it's important to realize that there are actually several different types of black hole, each predicted to form by quite different mechanisms. Perhaps the most familiar is a stellar mass black hole. These are thought to form as the endpoint of the life cycle of a massive star. Stars are thought to form by gravitational fragmentation of clouds of dust and gas, and so they can form in a very wide range of masses, from a tenth of the mass of the Sun to over 100 times that size. The most massive stars are very quick to burn through their available fuel in nuclear fusion processes, and once those processes falter, the star can no longer generate enough heat to counteract the self-gravity caused by its large mass, causing it to collapse in on itself and forcing the matter in the center of the object into some exotic degenerate states. At this point, the stars tend to explode in a wide range of exciting supernovae, but the ultra-dense core of the star can be left behind. If the total mass of that object exceeds about 3 to 4 times the mass of the Sun, then there's no state of matter that is dense enough to resist the pressure of gravity, and the material is forced into a singularity. But there's a second category of much, much more massive black holes that occur in quite different circumstances, with masses billions of times that size of the Sun. These supermassive black holes have been observed in the center of galaxies. Now, you may have seen this amazing image from the Event Horizon telescopes of the black hole in Sagittarius A star at the center of our Milky Way. This image has some special significance for me because my colleague, graduate student Joseph Farrar, was actually a member of the team that created this image. So how could such objects with such massives have formed? Did they start out as a stellar mass black hole? Did they simply become the remnants of stars that lived and died very early on in the universe that have simply been accumulating mass ever since? Well, it turns out there's a problem with that theory, and we know that because counterintuitively, supermassive black holes are in fact detectable. Black holes famously attract anything and everything that approaches them, but in general, the material doesn't fall directly into the hole. Instead, it spirals in, rather like water draining down a sink. In the process, the material forms an accretion disk around the hole so that it spirals in, and the closer it gets to the event horizon, the hotter that material becomes. And so it radiates then in increasingly short wavelengths of light, right up to gamma and X-rays. And since that radiation is emitted from the material in the surrounding disk, it's outside the event horizon, and it can therefore just about escape the gravitational pull of the black hole, allowing us to detect it. Astronomers have therefore gone and searched for these objects at these extreme wavelengths, and we've detected supermassive black holes in the center of active galaxies at very high redshifts, meaning that these objects have already existed less than 1 billion years after the Big Bang. But that's an issue if supermassive black holes started out as stellar mass black holes that simply grew by accumulating material, because then it should take roughly the age of the universe to reach the size that they are now. So where did these very early supermassive black holes come from? It implies that they form by a different mechanism, and for that reason we consider these to be in a different category from stellar mass black holes. But potentially black holes could have formed earlier still. The concept of primordial black holes was first proposed by Zeldovich and Novikov back in 1966. The conditions in the early universe could have led to localized regions of extremely high density, which, according to their calculations, could potentially collapse and form into black holes. Now, since that category of black holes don't form from stars at all, their masses could span an enormously large range, from 10 to the -8 of a kilogram up to 1,000 times the mass of the sun. Now, these have actually been considered as one candidate to explain dark matter, so detecting them is quite a big question in cosmology. But for our purposes, the key takeaway here is that not all black holes are alike. Various theories predict that they can form by quite different mechanisms. And so this is the reason why astronomers from several different branches of astrophysics are so keen to understand the population of black holes in the universe. The various theoretical mechanisms predict that the production of black holes with a wide range of masses for each of the different formation mechanisms. So if we can detect a large sample of black holes and measure their masses, then the mass distribution of that population should provide us constraints on their origin and their evolution. So it becomes a small matter of observation. Now, this is clearly a huge topic, and it touches on many branches of astrophysics. And if we covered all of the evidence for all three types of black hole, then this would be a very long talk. So instead, I hope this introduction has given you a bit of context for why I'm so excited about measuring the massive distribution of black holes. And for the rest of this talk, I'd like to focus on the stellar mass category of black holes, since those are most relevant to my research. So the question becomes then, how do we detect invisible objects? Well, there are a few telltale signatures that can give away even these most elusive of objects. And we touched on earlier the possibility of detecting signature of material falling into the black hole just before it reaches the point of no return. And the same principle can be applied to stellar mass black holes if they happen to form in a binary star. So if the partner star of the binary is in a close enough orbit with the black hole, then material of the star can be torn away and then it spirals into the black hole. On its way in, it forms an accretion disk, as we saw before. The friction increases as the material gets closer and closer in, causing it to heat up and then radiating ultimately in X-rays. This type of binary star is therefore known as a black hole X-ray binary, and they're noted for their outbursts, where they suddenly start to radiate very much more brightly for a set period of time, sometimes for weeks, before they drop back into a quiescent state. And we think that happens because the infalling material is basically lumpy. Although I have to say the accretion physics is extremely complex, so that's a bit of a generalization. So that's the first way that we can find stellar mass black holes, but it depends on them forming in a binary. Now, if both components of a binary star have evolved to the point where they've become black holes, then we recently acquired a whole new way to detect them, thanks to the advent of gravitational wave detectors like LIGO. If the black holes are in a very close orbit, then they can gradually lose angular momentum and spiral in towards one another, thanks to an ergosphere of material just outside their individual event horizons. And eventually that leads to the black holes merging, which can cause measurable cyclical distortions in space-time, which we detect as the gravitational wave signature. Now, here is a representation of that signature of a real-world detection from LIGO presented in audio format. It's a very, very fast signature, but quite distinctive. Now, the gravitational wave detectors can also detect black holes in binaries with neutron stars when those merge as well. And in both gravitational wave detections and X-ray binaries, we have a way of measuring the masses of the black hole involved because they happen to be in binaries and they can be measured from the dynamics. Oops. However, the presence of a binary companion in a system can substantially change the evolution of an object. So singleton black holes may have quite different formations histories. And it's estimated that about 30% of massive stars are initially single. Now, black holes can also become signal during their transition from a dying star. If they originally had a close-in star as a binary companion, that star can sometimes be engulfed as the dying star's atmosphere as it explodes as a supernova. And even if the companion star is far enough that it survives the initial supernova phase, the explosion alone can give the companion a natal kick and actually eject it from this binary system entirely. And singleton black holes are particularly interesting because since their formation, they will have evolved in an isolated way and are therefore less altered by interactions with any companion. And so they provide a direct probe of the black hole's formation. And so for this reason, it's important to be able to measure the population of isolated stellar mass black holes. But this leaves us with the challenge of how do you find an isolated stellar black hole? Any material it had in an accretion disk would be quickly consumed, so there should be no optical or even gravitational wave signature. And that's where the technique of microlensing comes in. So microlensing works by looking for the signature of the gravity of the black hole on stars in the background. In this movie, you can see the telescope icon on the left, which represents the observer on Earth, looking towards a source star on the right-hand side of the image. And in the middle, you can see a representation of a black hole. Though objects in our galaxy move very slowly from the point of view of an observer on Earth, they do move. And this means that eventually you do get chance alignments where one star passes directly in front of another. Since general relativity tells us that the gravity of the foreground object bends the space-time around it, the path of the light rays from that source star in the background are deflected around the black hole and creating images of the source, which move in conjunction with the relative motion of the objects. And in that sense, the foreground object is acting as a lens. Now, you'll notice that I have not mentioned what that foreground object is. It only matters that that object has mass and hence gravity. And significantly, the only light that the observer receives in this technique comes from the background source star, not from the foreground lens. And that means that the technique is capable of detecting objects that are entirely dark, including isolated black holes. And when this phenomenon occurs for stellar mass objects, the deflection of the light rays is very, very small, which leads to the name of microlensing. As a result, we typically don't resolve the two images of the source, and instead the lensing directs more light towards the observer than we would usually receive. So we detect this by monitoring the brightness of the background source star over a period of time, and we can see it gradually getting magnified as the lens approaches alignment and then demagnified as it moves away again. In addition to monitoring the brightness of the source star, the photometric signature, we can also monitor its apparent position or astrometric signature. This animation shows the same microlensing event from the point of view of an observer on Earth, looking directly towards the background source star. If we chart the apparent position of the source as a function of time, we can see that the apparent movement caused by the passage of the lens between us. Now, this animation gives an extreme example of the change in position of the source so that you can see it. In practice, the movement is extremely small. So to detect these two signatures, we can plot both the brightness of the source star and its apparent position as a function of time. Now, to give you a sense for the scale of these measurements, these figures plot the expected signature of an example of a 5 solar mass black hole located at 2 kiloparsecs from the Earth, passing in front of a background source in the galactic bulge. A few key numbers to take away from here. The characteristic timescale for these events is typically over 100 days, which in survey terms is quite a long timescale. Sometimes black hole events can actually last for multiple years. But the source star's brightness can be magnified by several factors, and that makes it relatively easy to detect in photometry. And the peak magnification is purely related to how closely separated the lens is on sky from that background star. It doesn't depend on the mass of the object or anything else. Now, interestingly, the apparent movement of the source star can be measured over a much longer time frame than the magnification of the light. But crucially, this signature is directly proportional to the mass of that lensing object. So a combination of the two measurements is a particularly powerful measure because the photometric signature by itself suffers from several degeneracies. Because we usually can't resolve the individual images of the source, the light curve of the event can look exactly the same from quite different objects. In this example, I've shown two events where the lens takes quite different trajectories relative to the line of sight from the Earth to the background source. And we can observe both the same photometric signature regardless of the relative trajectory of the lens and source if they're both single objects. And to give another example, because we measure the angular separation on sky between the lens and the source star, it's quite hard for us to tell the difference between a relatively low mass object that's quite close to us and a more massive object at a greater distance. Now, measuring the astrometric signature at the same time as the photometric one gives us a way to break those degeneracies, since it provides us with the information on the relative trajectory of the two objects. And that means that by combining both the photometry and the astrometry, we can measure not just the mass of the lensing object, but it's also its transverse velocity. And we can start then to measure the dynamics of these objects that are otherwise invisible. So microlensing events can tell us a great deal, if only we can find them. And that's not entirely trivial either. The technique quite literally depends on the chance alignment of two completely unrelated objects in the sky, which is intrinsically rare. This plot shows the rate at which microlensing events happen in different regions of the galaxy. Yellow on this plot is the areas where these events happen most often, and that's because we can see distant background stars behind a foreground population. And this is based on some models of galactic population dynamics. You can see that this is a log scale plot, so the odds of any given star being lensed is typically less than 1 in a million per year for most parts of the sky. But that said, microlensing is most likely to occur in those parts of the sky which are most densely populated, so surveys have traditionally concentrated towards regions in the galactic bulge, which is that region highlighted in the red box, and where we can see deep into the center of the Milky Way. A number of surveys have covered this region. They've now been in operation about 25 years, in particular the OGLE, MOA, and KMT-NET surveys. They provide the kind of long-term monitoring of a large area with the highest cadence reserved for the central bulge. But until recently, they couldn't monitor 24/7, so they issued discovery alerts to the wider community and encouraged observations by other facilities. And a number of follow-up teams responded to those alerts in real time to provide complementary observations at higher frequency. And this is the type of observation that Las Cumbres Observatory is ideally suited for. So this is where my team have been closely involved in providing those follow-up observations. Now, these ground-based telescopes don't have the spatial resolution high enough for the astrometry, so instead they concentrated on just the photometric signature. And they have discovered a wealth of events, including many planetary systems. And in recent years, these surveys typically report about 2,000 events per year. The vast majority of those are not caused by black holes, though. As you'd expect, the majority of the lens are simply stars in our galaxy passing between us and the galactic center. Nevertheless, one of the ground-based surveys, OGLE, provides an excellent, very long baseline data set for searching for events that might be due to black holes. And in 2016, Łukasz Wysockowski and his team searched this huge database looking for events with the characteristics of black hole lenses. He looked for events with the long timescale, over about 100 days, and the long baseline of the data set allowed him to rule out other forms of variability from the candidates he selected. That procedure identified 59 potential candidates, and the plot in the graphic there shows the spatial distribution of those candidates overlaid as the dark circles on a survey image of the galactic bulge in the center of the galaxy. This plot shows an example light curve for one of those targets, the photometry as a function of time. The green model, the curve in the background there, represents a classic microlensing event with its smooth increase and decrease in magnification. But when the timescale of the event is as long as this one, which in this case is about 2 years, we also have to take into account the microlensing parallax signature, which causes this additional sinusoidal signature in the light curve. Now, although both the lens and the source are extremely distant from Earth, typically over half the distance from us to the center of the galaxy, any subtle change in the alignment of the observer on Earth relative to the background star is clearly obvious. And an event this long, these waves are caused by the movement of the Earth in its orbit around the Sun. Now, Wysockowski took this into account when he modeled all of the candidate events, but the ground-based data alone were insufficient to break the degeneracies in the model and explicitly measure the lens mass and distance. Instead, they assigned the most probable values for these quantities by inferring them statistically based on models of the galactic population and dynamics. Now, they used those inferred masses of the lenses to estimate how bright the lensing objects would be if they were self-luminous stars. And in 13 of those cases, the light from the lenses of an object of that mass should have been detected in the ground-based data, but was not. That implies that the lenses were compact objects, meaning they're either black holes or neutron stars. But tantalizingly, that was as close as they could get with just the ground-based photometry alone. So near yet so far. And this was really the motivation for undertaking a search for the astrometric signature. But the amplitude of that signature, as I mentioned earlier, is so small that it requires much higher spatial resolution imaging. And the main factor in limiting the resolution of ground-based observations is the turbulence of Earth's atmosphere, which effectively causes blurring of the images of the stars. There are two ways to overcome that and achieve high-resolution imaging. The first is to use adaptive optics imaging, which is available from some large ground-based telescopes. And those facilities have been used to observe some microlensing events, but are typically quite oversubscribed. The other way, of course, is to use a telescope that flies above Earth's atmosphere entirely, such as the Hubble Space Telescope. Of course, this superb facility is also oversubscribed, but in this instance, the lead of this program, Kailash Sahu, is actually a member of staff at Space Telescope Science Institute, so it was natural for him to conduct the study using Hubble. So in 2009, Sahu and his team began a program to observe very carefully selected microlensing event with the Wide Field Imager 3 on the Hubble telescope. Now, I say carefully selected because Hubble has a relatively narrow field of view, just 2.7 arc minutes across. So it's very time consuming to monitor a large area of sky as the ground-based surveys do. Instead, the Hubble program relied on ground-based surveys to discover microlensing events and send out alerts while they were still in progress. Sahu and the team then narrowed down the selection by looking for those events with the characteristics of a black hole lens. Those would be events with long timescales for which the modeling of the ground-based data showed little or no light from neighboring stars and a high magnification. And over the course of the program to date, just 10 events have met the criteria for Hubble observations. After many years of patient observations, this program recently announced its first strong discovery. And 2 papers actually came out about the same target almost simultaneously in January last year. One led by Kailash Sahu, the PI of the Hubble program, and the other from an independent team led by Casey Lam. The Sahu paper concentrates on just one of the 10 objects they observed and concluded that the lens must be a black hole. And meanwhile, the Lam paper analyzed some of the same data for 5 events from the program in parallel and concluded that the same target must be a compact object, meaning at least a black hole or a neutron star. So let's take a look at the evidence. The target causing so much excitement goes by the catchy name of MOA 2011 BLG 191 and OGLE 2011 BLG 0462. That's because it was first discovered by 2 ground-based surveys simultaneously, MOA and OGLE, and the MOA discovery was announced slightly earlier than the OGLE one. The analysis of the ground-based data was performed in real time, and it fairly quickly revealed that this would be a good candidate for the HST program. It was predicted to have the long timescale characteristic of a black hole lens, and it had relatively few neighbor stars within the resolution of HST. The image you can see on screen is a reference image from the HST, showing the target in the center, circled in green, and the outer 2 cyan circles have radii of 1 and 2 arc seconds respectively, which is typically the best resolution we can get from Earth without adaptive optics. So you can see that from Earth-based observations, there would be a lot of blending of additional light from the neighboring stars. But from HST, the blending was quite low. And so the team asked HST to monitor this event at frequent interval or infrequent intervals over the next few years. And in the sequence of images, you can clearly see that the lensing star fades gradually as it changes in magnification. On the right-hand side, you can see the measurement of the brightness, the photometry, plotted as a function of time, the HST light curve. That's measured from the image sequence on the left, and that was used in the modeling of this event. At the same time, ground-based observatories also continued to monitor this event. The 2 surveys that found the event couldn't monitor it around the clock, so a team of other follow-up telescopes joined that effort to make sure that the light curve of the event was well sampled throughout, and my team were happy to contribute to that effort. Since this is ground-based data, of course, you can see that not all of the telescopes involved were fortunate with the weather during that event, and that tends to show up in the light curve as sections of data with higher scatter. Of course, HST was immune to that. But the distinctive feature of HST data is that it has such high resolution, we can use it to measure astrometry as well as photometric measurements. In this plot, you can see the red triangles, which indicate the measured position of the source star at intervals throughout the event. If the normal movement of the star on the sky had occurred without a lensing event, then these red triangles would line up on the black line. But you can see that the sources were deflected from that line as a result of the lens passing in front of it. Now, the position of the lens, which is inferred from the modeling of the data, is represented by the purple line. This is wavy not due to the lens movement, but rather because the observer was also moving during this event. Earth and HST were moving in orbit about the Sun, which subtly changes our line of sight towards the event. In this plot, the viewport is held fixed relative to the position of Earth. So we're effectively seeing our own annual parallax in the movement of the lens. When the event was analyzed, these position measurements were taken together with the brightness measurements from both HST and the ground-based telescopes. And it's from that combination of data that we can measure the parameters of the event. But frustratingly, the model parameters don't give us all the characteristics of the lens directly. The combination of photometry and astrometry measures the mass of the lens, but it determines only the relative parallax between the lens and source. That, and in turn, depends on the distance of the source and lens from Earth. So if we can measure the distance of either the source or the lens, then we can measure the distance of the other object. And fortunately, there is a way to estimate the distance to the background star, because unlike the lens, we do receive some light from it. Breaking the light of any star into its component wavelengths can tell us a great deal about its physical and chemical properties. This image shows a montage of spectra for different masses of stars and shows how the characteristics of those stars change as a function of mass. The dark lines in the spectra are produced by the constituents of the star's atmosphere absorbing light at those wavelengths. And the width and the depth of those lines are sensitive to the properties of the host star. So if we get spectroscopic data of high resolution, then we can measure those properties for the source star in the lensing event. And fortunately, this event was bright enough that high-resolution spectroscopy was possible, and that showed that the source star had a temperature similar to that of the Sun, but with somewhat lower surface gravity, which implies that it's a bit older than the Sun and a bit further along its evolution. Stars are conveniently quite predictable in their physical properties. The more massive they are, the hotter they are. And by comparing these measurements with theoretical models of stellar evolution, it's possible then to infer the absolute brightness of that object. We can then compare that brightness with the measured magnitude and use the difference between the two to estimate the distance to the source, and that then gives us the distance to the lens. So with all of these lines of evidence coming together, we can last take a look at the physical properties of the lens. And since two independent teams have modeled some of the data separately, I'm showing here the comparison of their results. The LAM team explored two different models, each of which used a slightly different weighting scheme to combine the ground-based data with the space-based data. So I've included both sets of those results. But one important caveat to note is that the Sahu team included additional data in their analysis, which is one reason for the variance in the results. They also used data that had been processed slightly differently. And subsequent analysis has shown that some of the data that the LAM's team used had some residual noise in it. And if you account for that, then the results agree with Sahu's paper results. But we can clearly say two very important things about the mystery lens that's causing this event. One is that we can say it's a massive object, several times the mass of the Sun. And two is that it's about 1.5 kiloparsecs from Earth, which in galactic terms is actually relatively close. And that's important because for an object that close, if it were producing light, then we should have been able to detect that light. Most astronomical objects that we know about do produce some light, and at that distance, we would have been able to see it in the data. But we can rule that out from the data that we achieved. So that means straight away that the lensing object has to be a compact object, a star that has collapsed under its own gravity to form some ultra-dense form of degenerate matter. Which means there are basically just three options. It could be either a white dwarf, a neutron star, or a black hole. Well, particle physics tells us that there's a theoretical maximum to the mass of the white dwarf can reach that before electron degeneracy is insufficient to support the star, and it collapses even further to become a neutron star. And that limit is 1.2 times the mass of the Sun. Now we measure the mass to be greater than that, so we can rule this out being a white dwarf. Neutron stars, meanwhile, are more dense and they can reach greater masses, but they still have a maximum mass for them as well. And after that, there is no force known in nature that can resist the pull of gravity. That mass limit is 2.2 times the mass of the Sun. And the mass inferred from both Sahu's models and Lamb's model is in excess of 2.2 solar masses. So that means it's highly likely that the lensing object isn't a neutron star. And that really leaves only one other option. The invisible object causing this microlensing signature had to be due to an isolated black hole. So I hope I've given you an overview of the detective story behind this first discovery. But what does that leave us in the wider context? I started out by saying that the reason for searching for black holes is to understand how they form. And we can really only do that by measuring a whole population of these objects, not just a single one. Measuring a single one doesn't give us much insight into the whole population. But so far, we've only been able to look at a very small field of view right in the center of our galaxy. So that really doesn't tell us a lot about the mass function of these objects across the galaxy in different stellar environments. So really, this search is just beginning. So what are the prospects for detecting more lensing black holes in the future? Well, it's quite a daunting technical challenge. To detect more microlensing black holes in this way, we'd have to regularly monitor the brightnesses of billions of stars distributed right the way across of our galaxy. In this picture of the Milky Way, the area surveyed by the HSTs so far is so small that it's actually smaller than the smallest red box that I could put on this image to explain it. And we need to keep monitoring all of those stars for years because those events last hundreds of days. We also need a large aperture telescope to do this because we need to reach very faint stars that are out at distances right to the center of the galaxy, and in order to probe as large a survey volume as possible. And there's an unfortunate trade-off between telescope aperture and field of view. And I stress that that's just to detect the events in progress. The astrometry is additional work, probably from another facility. Well, there is a telescope facility that's currently under construction that should help us to discover these events. This is drone footage of the Vera C. Rubin Observatory, which is currently being built in the Cerro Pachon summit on Chile. The telescope will have an effective aperture of 6.6 meters, meaning that it will be able to observe even very extremely faint stars. But due to its groundbreaking optical design, it will have a field of view that's 3.5 degrees on a side, and also have the spatial resolution sufficient to distinguish stars even in the very crowded regions in the center of our galaxy. That's wide enough that it can monitor a huge area of sky every night. This movie shows a simulation of one of the survey strategies under consideration. The chart on the left-hand side shows a map of the whole sky, and the colored dots you can see represent where the telescope is pointing at any given time. The movie shows a time lapse of just one night of observations of the survey in operation, showing just how large a region of the sky that it will cover per night. Now, the Rubin Observatory is due to officially start survey operations in October 2024, and it will continue that night after night for 10 years. That's more than long enough to discover a wealth of microlensing events across the entire sky, and we hope many more events caused by galactic black holes. So I hope I've given you a taste for why black holes are such fascinating objects and an insight into our very first detection of an isolated stellar mass black hole. So let me wrap up by saying that the future prospects for finding these most elusive of objects are looking good as new landmark facilities come online, like the Rubin Observatory, and we may finally be able to tell where these objects come from and how they evolve. And with that, I will say thank you very much for having me, and I'm happy to answer any questions you have.
Thank you very much. That was a great talk. We enjoyed it thoroughly. And now let me tell everybody that the floor is open for their questions. And I hope you see all the kudos that's coming your way through Zoom. Okay. Yeah, it's like the clapping's coming on one corner of the Zoom.
Thank you.
All look great. Yes, thank you very much. And also on the chat. So the floor is open for questions, and we already have a question. So you did mention that based on the mass of the lensing object, we could determine to a very good degree what it might be, what it should be. Now, you mentioned it's from the last few slides that it's an isolated black hole. Are we sure to rule out binary black holes or any other object any other black hole kind?
That's a really great question. There are some subtleties to the light curve that I didn't have a chance to go into, but if the lensing object is actually a binary object, then it is possible to detect that because it gives us an extra wiggle, if you will, in the light curve. And so we measure for we model it for a single object, and if that doesn't fit, then we can progressively add more terms into the equation and include the potential for a binary object. And it is possible for microlensing to detect binary objects as well as isolated ones. Yeah.
Perfect. Thank you. Next question wants you to elaborate on the importance of LIGO in your work.
LIGO is an amazing instrument. The LIGO Cagra detectors are really quite outstanding achievement. Really, the techniques are complementary. LIGO is particularly sensitive to binary objects where they merge and they send out the ripples in space-time. And it really takes an event as energetic as the merger of two black holes to cause a signal that we can detect here on Earth. And so LIGO is fantastic for exploring the population of binary objects right through from neutron stars to black holes, all of those things that we really struggle to find by their electromagnetic signatures. So complementary to that is the exploration of the isolated signatures. So they're both very important, and they both tell us a great deal about different aspects of the black hole population.
Perfect, thank you. And then in a lot of images that you showed, when a black hole, or let's say a compact object, is passing in front of a large object, let's say a galaxy, in addition to the light being blocked, we see it's distorted, let's say, right? So do we observe the same phenomena when a lensing object passes in front of a star? The distortion?
Yes, exactly. Yeah. So perhaps you've seen some of the beautiful Hubble and JWST images of galaxies that lens background quasars, and you see the quartet of images. That's effectively exactly the same phenomenon. It is the lensing phenomenon. Really the only difference that happens in the case of stars is that stars are so much smaller than a whole galaxy that the separation between those images that are created is too small for us to measure most of the time. So all we see is the brightness and the astrometric signature, which jiggles very, very slightly. The gravity of a whole galaxy is so much bigger and it's so much more distributed that you can more easily see those separate images. But it's basically the same phenomena at work.
Thank you. And in the beginning of your talk, you had a brief mention of dark matter. Now, there's a question about dark energy. Does this project inform the study of dark energy? Is that where it leads us to?
So the Rubin Observatory will make cosmological measurements and is going to be an important measure for dark energy. The technique I'm talking about is more specifically aimed at objects in our own galaxy, so not really far enough away to make those kind of measurements. But the measurement of the galaxy scale lensing, what we call strong lensing of background quasars. Now those are involved in the dark measurements, but that's a parallel technique.
Thank you. And you did mention about alternate methods to find the distances so that we could make a conclusion. Now, can you remind us how far did you measure these black holes to be from Earth?
So this particular black hole turned out to be 1.5 kiloparsecs from Earth. So about an eighth of the distance between the sun and the center of the galaxy, relatively close in galactic terms.
And another questioner wants to know if all these is inconsistent with general relativity, any anomalies you have observed, or will these observations result in discovering anomalies?
So in fact, general relativity has made some absolutely exquisite precision predictions about exactly what we should see in a microlensing event. And Einstein himself was doubtful that the phenomena would ever be detected because it was so small. But in fact, he was proved right despite himself. And in fact, it is detectable. It's completely consistent with relativity.
Thank you. And then you mentioned that you look for these objects in densely packed corners of the galaxy. What about globular clusters? And since they tend to have all the stars, do we ever observe black holes in globular clusters and the microlensing effect?
That's a great suggestion. Yes, we have looked for lensing objects in front of globular clusters. It's actually, as to the best of my knowledge, we haven't found one, but that's more in connection with the kind of population sample that we've managed to observe of globular clusters. So it's more down to a selection effect for the observations we've managed to take and not necessarily representative of the population.
Now, talking about the representation of the population, a questioner wants you to comment on the predicted distribution and density of the stellar class black holes in the Milky Way.
That's a very good question, because I have read a number of different theoretical predictions about the predicted population. And there are a number of different predictions that suggest something like 3 orders of magnitude in just how common these objects should be. And that's based on models of stellar evolution. So what we can say is, because we are looking for stellar mass black holes, we expect them to follow the spatial distribution of where the stars are in our galaxy. So we expect to see them when we look towards the galactic plane. And it's likely that they probably follow the distribution of stars in the galactic plane. But as for the distribution of the masses of these objects, or how common they are, really that's the outstanding question.
Thank you. And the next question is more of a personal question about where your studies are going to head perhaps in 10 years. Are you going to stick with microlensing or?
That's a fascinating question. I hope by the end of 10 years, we will be at the end of the Rubin survey, and I hope by then we'll have this huge population of events to study. So by the end of 10 years, I hope to be looking at those events. But I really feel at that point the field is open for those who are students now, who will be in a fabulous position to have this wonderful data set to explore at the end of the Rubin survey.
Yeah, speaking of that future of this kind of observations, having the predictions about the area and coverage and sensitivity of the measurements that you reported, can you project the rate of detections you expect from the Rubin telescope?
Not easily. So I showed a map of the galaxy showing the rate of predictions for microlensing event based on the known stars in the galaxy. So that's the main sequence regular stars in the galaxy. We don't have solid predictions of the rate of black hole events because the actual population of black holes is so unconstrained. So we expect it to follow the distribution of stars in the galaxy, but there's a very broad range of predictions of just how many events we should see. That's something that colleagues of mine are actually in the process of analyzing at the moment. So watch this space.
Thank you. And speaking of dark matter, is there a theoretical prediction on what fraction of the mass of a supermassive black hole could have arisen from dark matter?
Wow, that's a terrific question, and I must confess that is outside my area of expertise. So I'm not familiar with any of the predictions that have been made. Sorry.
Thank you. Okay, I believe I've covered all the questions so far. Let me go to the crew on the ground. Do they have any questions from the main speaker tonight?
Do we have any questions? I've got one, if no one else does at the moment. And that is, have you considered for astrometric data, looking at the history in the Kepler data and in the Gaia data for the kind of perturbations that you were describing?
Yes, absolutely. The Kepler data, precision of the astrometry, because of the size of the Kepler pixels, it doesn't quite have the same precision of position as we get from HST or from Gaia. But there is, I'm actually working with some of the teams that are analyzing the Gaia data, and the next upcoming data release from the Gaia catalog should include the time series of astrometric measurements to the point where the team is able to identify some events from it. So we are very excitedly looking forward to the next Gaia data release.
Any more questions here? Yeah, we've got one. I'm not sure she hasn't addressed that, but the question is, has anyone discovered or observed globular clusters looking for these wandering black holes?
Yes, certainly there have been many globular clusters have been observed by the ground-based surveys. We haven't found that many events from them. That's probably due to more the limitation in the observations that we have been able to get, and because they subtend a relatively small angular size on the sky, and so the number of the population that you're looking through towards that small area on the sky means the rate of events is relatively low. So we really have to look for a lot longer in order to see a small number of events, but it would be extremely interesting to find one.
Any more? Going, gone.
Okay, that concludes our question. Let me thank you very much again. Oh, there is one more question, actually, since we have James Webb upcoming. So is that going to contribute to your research, the data from James Webb?
Yes, James Webb will have, again, the beautiful astrometric precision of Hubble, albeit in the infrared rather than the optical. So it is definitely a candidate in the future for this kind of observations.
Perfect. Thank you very much, Dr. Street, for doing this talk. We're glad that you accepted it, and we're very happy.
Thank you very much.
We can have you in the future with more discoveries that you're going to share with us.
That would be a pleasure. Thank you for having me.
Sure. Perfect. Now, let me ask for the ground crew, do we have the WhatsApp presentation ready?
We have it up. We'll have to see if we can cast it to you.
And while you're doing that, let me actually remind everybody that Dr. Street is part of the Las Cumbres Observatory, and Las Cumbres Observatory has an educational program, which we are also part of. The program in our group that deals with LCO is called Cosmic Adventures, and every member is welcome to join. We have access to the 0.4 meter class of their telescopes. We could order images anytime we want. Actually, there's research currently going on about observing exoplanets in our group. So let me invite everybody to come and join. You could find the link and more information on our website, ocastronomers.org. If you go there on the resources tab, let me see, or on their special interest groups, SIGs tab, you will find Cosmic Adventures. And you will be able to send an email and join the group, and you'll be given access to LCO Observatory. So now let me see, looks like the crew on the ground got disconnected.
Hi, Reza. I'm sorry, but I don't think we're going to be able to get this to work in a respectable manner tonight. And out of respect to the people that are out there watching, I think it's just not going to happen. So what's up? Not up. Okay, sorry about that.
Okay, thank you very much, Alex. And I know you have put a lot of effort into preparing that. And I apologize to the audience and to you for keeping you holding and for not being able to make this happen. We'll do our best not for this thing to happen again. So let me just ask from the panelists, are there any final remarks or points that you would like to make? If not, I would like to thank everybody in attendance again, for people on the ground and also online. Hope to see you all next month with another great presentation. So check our website on ocastronomers.org for the events that we have. With this, everybody have a great night and good luck. Bye-bye.